Okay, welcome back. So now we're ready to start writing structures, Lewis structures for compounds. And we're going to start this lecture with how to write them for ionic compounds. And if you remember, ionic compounds were when elements gave away entirely or received electrons. So you're either giving away an electron or receiving an electron. One or the other. It's a give and take situation that usually occurs between metals and non-metals, like sodium chloride is the example I'll use, and they form salts. There's magnesium chloride, there's potassium chloride, there's all kinds of salts out there, and they can even be polyatomic, right? You can have polyatomic ions. And so how do we make ions? Again, we make an ion by, you can do this to an element or even a whole compound. That would be a polyatomic ion. Anytime you take away an electron or you give an electron to a substance, again, element or a compound, in this case we'll just look at elements, but anytime you give an electron or take an electron away from an element, you have an imbalance, and so you have a charge now. You have an imbalance of protons and electrons, and protons are positively charged and electrons are negatively charged. And so for ionic compounds, we're going to be giving away and taking electrons. Now, how do we represent the movement of those electrons using electron dot diagrams? Well, these are kind of tricky because they show the final result of the story, but they don't really show the story taking place. And so actually oftentimes you don't really see Lewis structures for ionic compounds in the real world. You typically only see them for covalent compounds where elements are sharing electrons, and you want to see, okay, who's sharing with who, because their complex compounds are quite large and complex. But ionic compounds, you just have a cation and an anion, and so in every case they always look the same. And here's how they look. I'll show you on my chalkboard here, and then I'll show you on my PowerPoint. But you notice if you look at the periodic table, sodium has one valence electron, right? As well as lithium or anything else in that first column. Chlorine's in column 7A or 17, and so it's got 7 valence electrons. Okay? And the way they work is, or the way they organize themselves is, remember, one on the top, bottom, left, right, and then start to pair them up. Well, you're eventually going to, I put these two side by side just so it would hopefully be appealing to the eye, and you would see what I'm trying to talk about here. If you're wondering why I didn't put the missing electron somewhere else, it really doesn't matter. Okay, it doesn't matter. But as long as I have 1 valence electron for sodium and 7 for chlorine, this will work. But I put them side by side so you could see something here. Wouldn't it be nice if sodium could just get rid of that electron, so it would have a full outer shell? Because underneath this shell is the second principal shell, which also holds 8 electrons, and that one's full. This is the third shell, right? Am I right? Is sodium in, oh, look at my shirt. Yep, sodium's in period 3, so in the third row. And so if you just knock that electron off, you'll expose the outermost shell, which will already be full of 8 electrons. So can we do that? And can we give that electron to chlorine, which would be happy? Sure, look, if we just add an electron right there, chlorine becomes happy because then it'll have its octet. All right, now you could do this. You could show an arrow, I guess. This is honestly how I think they should do these. You could show an arrow that goes from there to there, saying that the electron is going to move to go there, and that would be your structure. But that's really not how they do these. The way they do them is they actually move the electrons. The electrons actually get moved. So what we're going to actually do is take that electron away entirely, and we're going to draw it in its new location here on the chlorine. And then we're not done. Then what you do is you're going to put brackets around this where all the electrons are. You're going to put brackets, and then you're going to put the charge. Well, what's our charge going to be? We gained 1 electron, so we're just going to put a negative up there. So that has a negative charge. Now, we don't put brackets around the sodium because there's no electrons there. There is. It has 8, but we don't have to redraw those. It's just understood that metal will have 8 valence electrons there. We just don't show any because we had 1 and we took it away. But we give it a charge, though, now of positive. But you don't need to put brackets around it. And there you go. There's a Lewis structure for an ionic compound. So basically just replace the metal with different metals, replace the nonmetal with different nonmetals, and you have the same situation. Now they get a little more complex, so follow with me into the lecture here real quick, into the textbook so you can see what I mean. Again, let's first look at this example though. This would be the same example, but this time with potassium instead of sodium. Well, basically just get rid of its electron. It's not going to disappear. It's going to come over here to the chlorine to fulfill that octet. And then you're going to put brackets around the chlorine. You're going to put brackets around the anion and give it its charge. The anion's always negative, remember? And then the cation, in this case is potassium, you're just going to put the charge, but don't put brackets, and you don't have that electron there either anymore, remember? And so there you go. Magnesium oxide, the way that would work, slightly more complex because you're dealing with 2 electrons, but same thing, same procedure. You're going to erase both of those electrons and give magnesium a 2+ charge. You're then going to put those electrons on this oxygen atom, filling that orbital and filling that orbital, so that the whole oxygen atom has an octet, 2, 4, 6, 8 electrons. Put brackets around it and give it a charge. So you have to remember to put brackets around the anion that gains electrons. And you also don't put brackets around the cation. Remember that. And both of them need a charge. You have to put the charge. All right? Now, where it gets quite complex is if you actually have more than one cation or more than one anion. And that would happen when you have this example here. You see Na2S. So we have 2 sodiums in the ionic compound. Whereas up here, we were just dealing with 1 element and 1 element. Now, we still only have 1 cation and 1 anion, but we have 2 of the cations, right? It still has a binary, this ionic compound still has a binary structure in the fact that it has a positive component and a negative component. But for the positive component, you have 2 sodiums. And that's so that the charges will balance out. Remember, ionic compounds, the charges always have to balance. And so how would we show that? Well, you would just show a sodium on the right and a sodium on the left on like opposite sides of each other. Again, there's really no up, down, bottom, top, left, or right. I mean, a sphere doesn't have a top or a bottom or a left or a right, does it? So that's kind of what's going on here. If you were to put the sodium on the top and this sodium on the bottom, it'd kind of be the same idea as this, in the fact that they'd be opposite sides. So you want to put everything as far away from each other as you can, like this. Like if you're going to put a sodium on the left, put the other one all the way over here on the right. That's because since this sodium ion's positive and so is this one, they're repelled by each other. Remember, like charges repel. And then of course opposite charges attract. That's why we have an attraction between sodium and sulfide. This sodium ion is also attracted to the sulfide because of the opposite charge. You have a negative and a positive. But since the sodiums would be repelled by each other, you want to space them out. You want to show that. And that would even be the case if you had negative ions. So if you look at this example, calcium chloride, well, calcium takes this structure here with 2 valence electrons. Chlorine only has 1 valence electron. 1 vacancy in its outer valence shell. So it has 7 valence electrons. It just needs 1 more. So if calcium has 2, then what would we do with that other calcium's electron? Well, you would just have another chlorine and do the same thing. Put it all the way as far away from you can as the other chlorine. And so this would be your solution. This would be your final solution. Since calcium has to lose 2 electrons, it's going to give 1 to this chlorine and 1 to this chlorine. After that, put the charges, and make sure to remember to put the brackets around the anions that gain electrons. So the molecular formula would be CaCl2, calcium chloride. Now, that helped us in making a prediction, didn't it? Let's say we didn't already do chapter 5 where we learned how to make write molecular formulas and deal with charges. Let's say we didn't have any of that exposure, but we started the year out with this chapter, which I've been tempted to do almost every year. You would already be able to tell, like visually, pictorially, that, oh, well, if this electron is going to go to this chlorine, there's still this electron that needs to be dealt with, and so I would need some other anion. If we're just dealing with calcium and chlorine, then I just basically just going to need one more chlorine to make that work. And so here you go, there's your salt. And the way that'll work, check this out. This is, oops, wait, yeah, I have to do that, and then this. Watch this. Calcium chloride formula unit. If you remember from, I don't remember what chapter this was, but we talked about how ionic compounds come together, and the way they do that is they form like these formula units like this. So basically, for every calcium, you're going to have 2 chlorines. You're going to have 2 chlorines on either side. And so the crystal arrangement would be like this. All right, here's a better one. Wait, is that? Yeah, calcium, and you're going to have 2 chlorines around it. But remember, this chlorine will be attracted to the next calcium as well. And so this would be like the crystal lattice. Everything's spacing themselves out as far away as they can. This would be the crystal lattice, which at the end of the day ends up being cubic, just like sodium chloride. But you get different crystal lattices based on the geometry and these angles here, which is what we're going to talk about later on in the chapter. But the point I'm just trying to make is as the calciums and the chlorines come together, they do so in this like lattice shape. Now I don't like this picture though because they're showing lines. Technically there's no lines because lines are used to represent shared electrons. So that would be like a criticism I have of that picture. Technically they just sit next to each other like this, like sodiums and chlorines just sit next to each other like that accordingly. Or if you do draw a line, what you do is you color the line like this so that everyone knows. That's kind of the standard. Here you go. Perfect. See how they don't show the lines really? They show the lines to kind of show the cubic shape, but basically they're just showing you the arrangement of the cations and the anions in this 3D lattice. Here's calcium fluoride. Again, at the end of the day, a lot of them end up being cubic, but they just basically sit next to each other, and in this case they would just sit side by side like this. All right, so you should be able to do multiple examples of ionic compounds. Remember to make the metals lose their electrons. That's obvious because you'll only have 1 or maybe 2 of them, and they're pretty easy to get rid of. And make the nonmetals gain electrons because you're just so close to fulfilling the octet rule that it's just easier to gain. In this case, sulfur would need to gain 2, wouldn't it? And so I can only gain 1 though from sodium. So how do I do that? We'll just add another sodium. And there you go. But at the end of the day, we have an octet, we have an octet, and we have an octet. The reason I don't like these is because they don't actually show the octet there, do they, around the sodium, but it's technically there, remember? We talked about that. Okay. So that's going to be it for writing Lewis structures for ionic compounds. I'm about to put a 4 there and replace the word ionic with covalent, finish that video, and then start filming the rest of them tomorrow. But I wanted to give you guys enough to start the week out strong. All right. Bye-bye.